In this devlog, we'll take a look at how to implement the backpropagation algorithm for our neural network. And the way we do this is we take the error value, the total error value, the same value that we computed last time, and examine how much contribution the weights of our neural networks actually, how much our weights of the neural network contribute to this error value. If we know that particular amount, then we can use that amount to attempt to lower the error value, and by means of adjusting the weights according to that delta difference. Now, there are a lot of mathematics involved in it in terms of proving how backpropagation algorithm works, but for this video, we'll focus on the actual implementation. And I've pulled up my guide here that will serve as a as the numerical process, or checking if, or the manual process on how backpropagation is actually implemented, so we can translate that to code. And according to this guide, we start with computing what are called the gradients in relation to the derived values of the neurons in each particular layer. Okay, so we'll take it step by step, and we'll first start with the output to the hidden layer, or computing the gradients from the output layer to the first adjacent hidden layer from the output layer, because sometimes your neural network can be stacked and you might have multiple hidden layers. So regardless of that stacked setup, the first step is always to compute from the output to the hidden layer. So to compute the gradients from the output to the hidden layer, the equation is pretty straightforward. The gradients can be computed by taking in the product of the derived values for our guess in the output layer, or that would be our y values. We get the derived values, which we can already do by, I think it was the matrixify derived values function of a given matrix, or of a given layer, and multiply it by the individual errors, which we already stored as a vector of double numbers. Okay, so once we multiply that, we don't really multiply it, but rather we take the product of each element of those values and store it as an array, or more specifically a matrix with 1 row and 3 columns in this example, as the gradient values for the output to the hidden. So that's what we'll try to implement first. So in our neural network, maybe we can have something like, okay, we have a vector of matrices for our weight matrices. We can also have a vector of matrix for our gradient matrices. Right? So we want to represent the gradients as not as vectors, but as matrices as well, so we can multiply them the way we would multiply any matrix. Okay, so in that case, we have to initialize it. We have to initialize it. No, actually, we don't have to initialize it yet. In that case, we can have a backpropagation function similar to what we had for the feed forward. So we say void propagation. Right? It's the void function, and it will play around with the values that are internal to this neural network. So going back to our implementation, just zoom that out. We say void neural network backpropagation. Right, and let's just label this as the output to hidden. So the things that we need are the derived values of the output layer. Okay, so we know that for a given layer, we can extract those derived values by calling the function matrixify derived vals from the class layer. And we know that we can get the output layer by using the output layer index, which is computed by this layers.size, similar to what we did with the error. And we can say that the vector of matrix pointers or sorry, what's that? Right, so it's just a matrix. So the matrix corresponding to the gradients, right, of output to hidden, so for out to z, or I'll call it y to z. Okay, so the gradients from y to z represented as a matrix is equal to this layers at output layer index, and we get the matrixified derived vowels. So matrixified derived vowels. Okay, and that will give us the this is just the derived values, not the gradient set, but rather the derived values from y to z, or from output to hidden. Okay, once we have that matrix, that this variable, this matrix of values, is actually this one. Okay, and then for our error function, we actually loop through. Yeah, so what we'll do is we'll create a new matrix with the same size as the output values. So we can say gradients y to z is equal to a new matrix of size of one row and whatever the size of our output value is. So that would be this layers at output layer index of a function to get the size dot size. I guess this one is a public, no, it's private. So maybe I need a, well, you can always do something like get neurons dot size, right? So it will return to us the number of columns, the size of the neurons in the output layer, and use that value as the number of columns for the gradients matrix. Okay, and then what we can do is we can loop through the errors. So this for int I equal to 0, I is less than this errors dot size I plus plus. Okay, so remember, in our neural network we had an errors variable which consists or which represents the vector of errors for each output neuron against the given target. Okay, so what we do is we multiply. Okay, we know that this is only a matrix of size row 1, so we can get the value, we'll call it d, from that matrix. So derived values y to z, forgot the function, I think it was get val, yeah, get value. So derived values y to z, get value row 0 at column I. Okay, that will be the derived value at y, so that will be each of these things, okay, which we multiply to each of the errors. So double E will be the errors at index I, and the product, let's call it P, or let's call it G because that's the actual gradient, is equal to D times E, which we then push to gradients y to z. And I believe we had a value, set value, I think, right? Set value, okay. Set value at this is just a one-dimensional thing, so it's always row 0 G, or rather, sorry, column I, value G. Okay. So this particular part from lines 8 to 12, or rather from lines 8 to 13, this one simply computes this part. We get the derived values of y, multiply it by the error, by the individual errors, right, and then get a vector, in this case a matrix with one row of gradients, right, and store it in gradients y to z. Okay. Now we'd like to systemize this process similar to what we did with feed forward. Right? And feed forward, we're looping from the innermost or the leftmost layer down to the output layer. So we can actually do the same thing for back propagation. Right? We loop through, we don't really need to loop through the output layer because we already computed it here. So the next step would be to loop through int I as our counter will now be the index of the first hidden layer left of the output layer. So that would be output layer index minus 1, right? Which is the index of the layer to the left of the output layer. Okay, so index I equals that one. And what we'll do is our condition for the loop will be that I is greater than or equal to 0. And we keep subtracting I. Okay. So what we're doing here is we're moving from last hidden layer down to input layer. Okay, but before that, I think I missed a step, which was to compute the actual gradients. Alright, okay, so we already computed the actual gradients here, and now to compute the delta weights. Right, so the delta weights are are the difference values of how much these weights contribute to the total error of the neural network. Now we can compute the delta weights. The delta weight size is actually the same size as the corresponding weights for the consecutive layers. So in this case, the first delta weight will be the size of the first delta weight will be the same size as the weight matrix between the last hidden layer and the output layer, which we can compute by multiplying the transpose of the gradients we just computed multiplied by the derived values of the last hidden layer. Okay. So the last hidden layer again can be computed by output layer index minus 1. So I guess it would be good to store it as a variable. Okay. So last hidden layer index is equal to output layer index minus 1. We can get that layer, last hidden layer, by saying this layer's at last hidden layer index. Okay, once we have that, then we can get the z values. So it's not the derived values, rather it's the actual activated values for that layer, the z values. So we can say well, we need a matrix. We need another matrix to store the delta weights, right? So we say something like matrix delta output to hidden is equal to a new matrix. I think I forgot something for constructing matrices, and that would be to set everything to 0. So I don't want it to be random. So I'll say false for this one, right? So it will create an empty matrix. Same for new matrix. This one will have the same size as the weights. Okay, so we should be able to get the weights of the neural network by using the variable weight matrices, right? And we know that the weight matrix index for the last hidden layer, the weight matrix in between the last hidden layer and the output layer will be oh, we can actually just get it from the okay, let's extract it first. We have a vector, no, rather a matrix of weights output hidden is actually from this weight name of the variable weight matrices. Okay. This weight matrices at output layer index, okay, it's the index of the last output layer minus 1. Okay. All right, so once we have that, we can construct a new matrix we have a function to get the number of rows and columns. Yeah, get num rows. Get num rows. Okay, just to make the code a little bit cleaner, let's just format this a bit. Okay, create a new matrix with get num rows, get num columns, and I want to set it to zero initially. Right, so we have something like that. Okay, so that's the delta output to hidden, right? Which is a new matrix, and to get the result, well, actually we don't really need to construct a new matrix. What we can do is we can use our multiply matrix, this one, multiply matrix function. Right, I forgot we had this thing. So utils multiply matrix, right? Yeah, that command pattern function. And new, something like new. Okay, pass it two matrices. In this case, the two matrices will be the gradient. The transposed gradient, so gradients y to z transpose. Okay, remember we actually had a transpose function for our matrix. Matrix transpose right there. Okay, so gradients y to z transpose and the values of the last hidden layer, which is also a matrix. What we want is the activated vals, which returns a matrix. So we say last hidden layer, matrixify, pull up that thing so it will do autocomplete, matrixify activated vals. Let's clean this up. New multiply matrix, just so we can see the arguments. It's the transpose of the gradients, the matrix of activated vals for the last hidden layer, and we say execute, okay, which will give us our delta output to hidden. Okay, now that's a lot of code, so let's just make sure that we're able to compile this thing. Okay, matrix says no member name transpose. I forgot an S right there. So transpose. Let's try to compile this. Okay, compiled successfully. Let's see if it actually runs. In my main function, okay, after doing the feed forward and printing the console, we can run back propagation. This. Okay, so it seems to have no error. Right, so we can continue on code. Alright, So now that we have the delta output to hidden, right, we actually want the transposed version of delta output to hidden, right? Because we multiply this, for example, this one, a 1 by 3 matrix transpose becomes a 3 by 1 matrix, multiplied to the matrix of hidden activated layers, activated values. It becomes a 3 by 2 matrix, right? That's this one. Now, since 3 by 2 matrix isn't really the form of the weight matrix between the last hidden and the output layer, so we have to transpose that, so it becomes a 2 by 3 matrix, right? Which is already the same as our weight matrix from the hidden to the output layer, which is a 2 by 3 matrix. So aside from executing it, we should also transpose the result to give us the final delta output hidden. Okay. So now that we have that, we can then adjust the weights of our of that set by simply subtracting the values in the original weights minus the delta weights. Since it also has the same form, then subtracting it will be as simple as looping through each value and subtracting each value with the same row column index of the delta weights. So we'll before that, I'll create a new vector of matrix pointers which will correspond to my new weights. Okay, and what we'll do is we'll reverse this later on, because remember, we're moving from back propagation to forward to the from the output layer to the hidden layer. So once we compute the delta input, we can compute for the new weights output to hidden, whose size is equal to a new matrix of of delta output to hidden. So we can actually use that now. Get num rows, get num columns, false, let's just format this quickly right here. Okay, so new weights output to hidden will be an empty matrix, and what we'll do is we'll loop from r equals 0 row wise less than delta output hidden get num rows r plus plus, and then loop column wise, change all r's to c, change rows to cols. Okay, four. Yeah, so loop through the size of the deltas, and then new weights output to hidden set value, right? Set value at RC will be equal to, extract that, double new weight is equal to the original weights, which can be found in weights output to hidden. I keep forgetting the name of the functions we created. Get value, so it's get value set value. Okay, get value at RC new weight. You can also have delta weight from the delta output to hidden. Get value RC, which is the same thing, right? Same indices. Set value to original minus delta. So in this case, sorry, this is not new weight. This is original weight. Okay, so the original weight, delta weight, so it's the original minus the delta. So it would be original weight minus the delta weight. For our new weights output hidden, once we're done with that, we can push it to our new weights matrix. Okay, so after doing that, we say new weights matrix pushback new weights output to hidden, new weights output to hidden, right? Okay, let's see first if this actually works. Let's try to compile it. Might have some syntax errors. Okay, no syntax errors. Let's try to run it. Okay, so everything seems to be in order. Okay, before moving to this particular loop, let's go ahead and just examine if the weights indeed adjusted. Okay. And we can do this by simply printing out the new weights output to hidden matrix. So we can do something hackish or something. I think it was print the console. Okay, just so we know this one is actually printing the console. We can say cout output to hidden new weights. Right? Let's try to see if this works. Okay, so we can see that let's examine this part. Yes, it actually adjusted the weights. Right? So this is the weight matrix at between the output layer, the last hidden layer, and the output layer, and this is the new weights for that weight matrix. Okay, so we can see that from 0.103506 it went to 160075, 24 went down to 20, 93 went up to 99, 0.9 went up to 1, which is kind of weird. 89 went down to 84, 40 went up to 46. So the weights actually adjusted according to that delta value. So let's try to continue on. Now for the hidden to the input. Okay, so for the hidden to the input, the first thing we have to do is it's actually pretty similar. Okay, instead of getting the activated value, or rather the derived values for the output layer, we now get the derived values for whatever hidden layer we're in. Okay, so maybe that's the first step that we have to do. We need to extract this in the form of a matrix. And we can see here in this part of the code that we're already looping through that, right? So we can say that the layer L will correspond to each layer. Actually, I don't think we need to include we don't need to include the input layer since we won't be adjusting it from there. So layer L will now correspond to each hidden layer in our neural network. So we can say layer L is equal to this layers at index I. Okay. So to get the derived values for that layer, we just say matrix derived hidden is equal to L, and I keep forgetting the name of the function, matrixify derived vals. So matrixify derived vals, okay, which will return to us a matrix of derived values for this particular layer, in this case layer L. Okay. So we have our variables in place in the form of a matrix. Now we need to compute for the gradients. So again, the size of the gradients will always be equal to the size of the of the hidden layer, the current hidden layer we're in. So we can say that we have another matrix of gradients that we'd like to compute. So we say gradients derived, or derived gradients. Yeah, this obsessive compulsive thing wherein I want all my equations to be nicely aligned. Okay, so matrix derived gradients is equal to a new matrix. Well, actually, actually, we won't keep a variable for that because according to this, we compute these gradients by doing this portion first. Okay. Now, I'm not the best mathematician, so I think this notation isn't valid. But in my mind, the way when I wrote this particular equation, in my mind, I actually understand it, or it's the way I understand the particular process. The way I understand it is that to get this particular term, okay, we get the gradients in the output layer, or the gradients to the right of the current layer, and multiply it by the sum, or rather sum everything. Okay, sum everything, or rather multiply those values to the weights that span out from the current neuron in the neural in that particular hidden layer. So what I mean by this is, if you look at the diagram here, the weights that span from the hidden neuron, or the neuron in the hidden layer, will be, let's say for this Z1 hidden layer, that will be these weights right here. In this case, weight 7, weight 9, and weight 11. Now, to systemize that, we simply say that the index for this neuron is equal to the row index for the matrix, for a given matrix, right? Or rather, the of the weight matrix to the right of the hidden layer. Okay, so each of these indices represent the index of the row of the weight matrix to the right of this hidden layer. So we can actually get, right? We can actually get the weights that span out of it by simply getting the columns, right? The columns for that row index, and we multiply it against the gradients for each of the neurons to the right of that hidden layer. In this case, that would be the gradients for the output layer. Okay, so that's what this term means. Where's that? Yeah, so that's what this term means. And to get that, if we have that matrix of gradients, what we can actually do is we can get the transpose of the columns only of that row, right? And then just multiply everything. So just to save us some time, maybe what we can do is okay, I guess I'll initialize this new matrix, wherein the number of columns will be let's see, derived gradients. How did I do it in the first one? Well, the first one, gradients y to z, right? Gradients y to z, yeah, we'll always have a row of 1, right? And then the size of the column will be the size of the hidden layer. Okay, so what I can do is this one will always be 1, and then we'll say L get neurons size to give us the number of columns, and say false. Okay, so this will create an empty derived gradients matrix. And then what we can do is we can actually loop against that empty matrix, setting the necessary values. So we do a for loop for, in this case, r is equal to Well, actually, we can just loop, to save us some time, we can just loop column wise. No, we have to loop row wise. Let me just analyze this a bit. Okay, we need it in the form of a matrix. But then, let's see now. Well, actually, that's the first term, and then we have to multiply it to the derived values of the current hidden layer. Yeah, just think about this for a moment. Okay, so maybe what we can do is we can loop. Well, I know I have to loop row-wise because I need to get the columns here. So maybe what I can do is I can get the weight matrix. Okay, what I'll do is I'll check first if I'm in the hidden to output, or I'm in the last hidden layer. So I'll check that if I is equal to output layer index minus 1. If I'm in the last hidden matrix, I'll do something, and then else all others I'll do a different process. So okay, so if I'm in the last hidden layer, okay, so if I'm in the last hidden layer, if I'm in the last hidden layer, then okay, my gradient outputs will be this thing, gradients y to z, from this part right here. Okay, so I can loop through them and get the value, right? R is equal to derived gradients get, or rather 0, sorry, 0, R is less than derived gradients get non-rows, R plus plus. Let's make sure I'm not looping column wise anywhere else. Okay, the same thing, substitute R for C, R for C, for substitute rows with calls. So now we're looping column wise against the derived gradients. Oh no, maybe they do the same thing for this one. Oh, it's all good. All right, so we're looping against all the derived gradients. Okay, so now we have an index row. Okay, so what we want are these values right here. Should I have looped? Transpose of the weights. I really need this. Or can I just do... Can I just multiply it one by one? Yeah, I think I can just multiply it one by one. Okay, so... I'm sorry. I need to loop against the... Will it really matter? Yeah, I guess that's the question. Will it really matter? Okay, weight matrix. I need the weight matrix. We'll say matrix, weight matrix is equal to this weight matrices at index, output layer index minus 1. or rather I think, or I minus 1. Okay, what I'm trying to do is I'm trying to get this weight matrix. Okay, if I'm here, okay, this is index 0, index 1, index 0, index 1. So if I'm in this layer, the index of the weight matrix will always be equal to the index of the hidden layer. Okay, so I guess it will be I. Okay, and I don't, do I need this? Do I need to check if I'm in the, oh yeah, I need to check. I need to check if I'm in the output layer index minus 1, because I'll change derive gradients to weight matrix. Okay. Deceived gradients. Weight matrix. Okay, so I'll loop through each weight matrix because I know that index R will correspond to, index R will correspond to this one, right? So I can get all the gradients. I see, all the gradients in the output matrix. So I need to store the gradients as a vector of matrix of gradients. I think that's what I missed. Gradient, so after I compute the gradients y to z, I store it. Right, I store it. Gradients at I. Or I can just play around with the gradients. No, I don't. No, I shouldn't play around with the gradients. Oh, no. Yeah, I got it now. I can just have a matrix of gradients. Matrix gradient. Okay, so that will be my counter for the gradient. So I can just say something like, and once I compute the weights, blah blah blah, I can just say that the gradient will be equal to, what will it be equal to? Gradients. No, not gradient matrices. Gradient is equal to gradient. Gradients y to z. Or more specifically, I'll create a copy of the gradients from y to z, get num rows, gradients y to z, get num calls, false. Okay, and then I loop through that. So it's the same as this one. Okay, but instead of delta output to hidden, it's actually gradients y to z. Right, so I'm looping through the gradients y to z and just copying the column, the value, set value of gradients y to z RC, index RC at RC. Just copying that value and setting it as the gradient, as current gradient. Okay, so that gradient variable will serve as, I don't need to check wherever I am here, because I need to use the gradients to the left or to the right of the current hidden layer. Okay, so once I have that gradient matrix, what I can do is I can loop against the weight matrix, and then use the value, okay, for each of the, okay, so now I make row here, row column here. Okay, so I need to have a sum, double sum is equal to 0. Okay, and that sum will be the sum of the products for each gradient value. Okay, I get it. For each gradient value, so not this gradient, but rather gradient at RC, or rather gradient get value at index RC, okay, times the weight, right? The weight, in this case, the weight matrix get value at index RC. Does this make sense? Right, I think it makes sense. Hopefully. I'll call this a double P. Okay, so we're multiplying the gradient value. And again, gradient matrix here represents the gradient matrix to the right, right? The gradient matrix to the right of the current hidden layer. Okay, so initially it would be set to the gradients from the gradients y to z, and we'll proceed to move on as we update it. Okay, so so we have that, and we say sum plus equals p to get the summation of that. Once we loop column wise, then we can set that for the derived gradients. Let me just see if this is correct. We're looping against the weight matrix, row wise, column wise. Okay, the index R in this case will be the column index of the derived gradients. Okay, so I think I got it. So this means that derived gradients set value at row 0. It will always be one row, and then at column index R, okay, the new value will be sum. Am I correct in? Well, more specifically, sum, that's this term right here, times the derivative of right, the derivative of the current z. So L, let's have that as another variable. So the gradient value, so gradient g, is equal to the sum, the summation term here, multiplied to the derived value at neuron index. What's the index of that? These layers, or layer L. Can I do this? Get neuron layer HPP. Set neurons. Well, I can actually just get the activated vals, right? Matrix activated vals is equal to activated hidden is equal to L matrixify activated vals. Okay, so instead of using L, I can say activated hidden. Now I want to get the value at, to always have one row. R. Is it R? Weight matrix. get non-rows. All right, so weight matrix will be the, so I think it's also R, right? Because index R, because the index R is the row index of the weight matrix, which is the weight matrix to the right of the current hidden layer. Okay, so we're sure that the number of rows in that matrix is equal to the number of rows in the, equal to the number of neurons rather in the current hidden layer. So we can use R as that index. Okay, we always have one row, so we use index 0 as the index for that row. Okay, so derived gradient set value 0R G. There we go. Gradients. Okay. So that will be this G right here. And then to get the delta weights, we multiply the transpose of those gradients. So that will be the derived gradients right there after doing all those crazy loops. And multiply it to the neuron values, the raw neuron values, to the left of the input matrix, or rather of the input matrix, medications kicking in, of the current hidden layer. Okay, but we have to check, because if we're not looking at the input, because the input doesn't have any derived values, so if we're not looking at the input, so that's where we can have the if. Oh, but before that, we have to declare a delta weight. Anyway, we'll say, okay, here's what we'll do. We'll create a new matrix and call that the left neurons matrix. The left neurons matrix will be equal to this layers at index I minus 1. Okay. Get, or rather matrixify, activated vowels. Okay, so by default, if you have a stacked neural network, it will get the activated values of the left hidden layer, because it's still a hidden layer, so it's still the z variables. We still need the activated version of those variables. But then we check if, okay, if I minus 1 is equal to 0, I think we can do it in one go. We want to check if we're in the input layer, and we can check that by checking if I minus 1 is equal to 0, meaning we're looking at the index of the input layer. Okay, then left neurons is equal to this layers at 0 matrixify vowels, not activated vowels, but vowels. Else, it would be this layers at I minus 1 matrixify vowels, matrixify activated vowels. So get the left neurons for that. Is it matrixify vowels? Yes, matrixify vowels. Okay, so that means for the left neurons, because we need that to multiply our matrix. So we now have gradients Wow, so in that case, we didn't need this one, because we can instantiate it here. So derived gradients is equal to utils multiply matrix, rather new utils multiply matrix. The one we should pass will be the gradients that we just computed, the derived no, not derived, oh man, we needed that derived gradients. What I meant is we need the delta weights, right? Delta weights is equal to new utils multiply matrix, and the one that will pass will be the transpose version of the derived gradient. So derived gradients transpose and the left neurons. Execute. Need to transpose it for it to get the same form, so we do transpose. So we transpose the result, which will give us the delta weights. And once we have the delta weights, once we have the delta weights, we can do the same process. Or rather, we need to create the new matrix first, right? Which has the same size as the delta weights. Okay, so we create a new matrix and call it new weights, which is a new matrix of size. Number of rows is equal to delta weights get num rows. Number of columns is delta weights get num cols, and false because we want to set it to 0 values. All right, so new weights is equal to a new matrix with the same size as delta weights, and then we can loop through that new weights. So for r equals 0, r is less than new weights get num rows, r plus, we loop column wise, c is equal to 0, c is less than new weights get num cols, c plus plus. We set the new weights value. Let's do it piece by piece. So we get the value of the delta weight, so we'll call it d, for example, from delta weights get value at RC. Okay, we get the value at the what was I doing? no, sorry. This should be weight matrix. Okay, but we want the weight matrix. Okay, this weight matrix right here is the weight matrix to the right of the current hidden layer. What we want is the weight matrix to the left of the current hidden layer. Right. So we say matrix I minus 1. Right? Let's say original weight is the weight matrices at I minus 1. Okay, so we say original weight double W get value at RC. We know that it has the same weights. Delta weight is new weights, or rather delta weights get value at RC, and we do the same subtraction, which is we subtract the original minus the delta. So the original will be W minus the delta. So we need to do something like that. And we say double N, which is the new weight, is equal to the weight minus the delta. And then we set that for the new weight. So we say new weights at, or rather, set value RCN. Hope this is correct. New weight set val RCN. Now we have the new weights, and then I think we need to do one more thing. Two more things actually. For the new weights, we push it to our matrix of new weights. Okay, so we do new weights, push back. do I end the loop? Right here. So we say new weights. Oh no, I think I redeclared the variable, right? Oh no. Let's use a different variable for new weights here. Instead of new weights, we'll call this new weights hidden, for lack of a better term. Replace new weights with new weights hidden. Right. There we go. Okay, so new weights set, or rather push back new weights hidden. Okay, so we push it to our array of new weights. And then what we do is we need to set the gradient value for the next loop, right? So we do something like this. So gradient will now become a new matrix again, but this time following the gradients for new gradients. Right, so gradients will be a new matrix, but instead of gradients y to z, okay, this is a bit tricky. What did I use for? I think it was derived gradients. Right, derived gradients. It's derived gradients instead of gradients y to z. Gradients y to z now become derived gradients. Okay, then it'll continue its loop, continue looping until it finally ends. Hopefully this compiles. It's a lot of code. Right. Okay, line number 52. Okay, instead of at, what line was that? 92 or 96? Okay, no, it's not at, it's get value. So this one should also be incorrect, I guess. So you don't have an at function, you have a get value function. Let's try to compile this. Okay, let's try to correct this error, line number 93. No, line number 90, it's not, line number 74 rather. 74. Okay, this should be, this is a vector, so you can just do at. This is a vector as well, so at. Let's look for all instances that use arrow at. Okay, no more. Let's try to compile it again. A few more errors, line number 63. For r equals 0, this should be int r equals 0. This should be int c equals 0. Same goes for this one. Okay, I'll try to explain the code line per line again. Just have to make this compile properly. Maybe I have one more neural network. Back propagation, line number 92. Push back, this is a vector, so we can just use the dot notation. Alright. Try to run it, make sure that we don't have any index out of bounds. Okay. Now, this is going to be hard to debug. We're going to do it by means of trial and error. Problem in dealing with a lot of loops. Still out of bounds. Oops, sorry. Guess it wasn't there. It's probably here. Let's remove this chunk of code. Okay, just to see if where we actually had a mistake. Still out of bounds. Probably here. Okay, so our our error is probably at this part. Y I minus 1 will never reach 0. Output layer index minus 1. If it were 3 to 3 neural network, 2 minus 1, 1 minus 0, 0. Oh, okay. Yeah, it's this part. Our weight matrix should correspond to the weight matrices at I. Since we're in the output layer, let's look at the diagram again. Since we're in the output layer, 0, index 0, index 1 will never reach this part. So if we're here, the weight matrix will always be this one. Oh, I see now. Yeah, it will always be this one, right? That's why we said that if we do 0, 1, then weight matrix is 0, 1. So if we're here at layers index 1, the right layer, which is represent the right weight matrix, will be represented by the same index I. If you wanted to get the original weight, which is the matrix to the left, it should be weight matrices at I minus 1. That kind of looks correct. So where did I get an index out of bounds? Let's try to print out where we actually are. Alright, so we got the 1. Right, we got 1. So this one holds true. Original weight left I minus 1. We still have I minus 1, 0. So this should have been correct. Let's see if we reach this part. Okay, so so I didn't print out. This thing didn't print out. So we're somewhere stuck here. Right, so weight matrix, get row num rows, get num calls, okay, let's see where we are for each loop. We're actually stopping, right? So I'll print this in the form of R C. So that's where it's coughing up an error. Okay, so 0, 0, 0, 1, 0, 2, 1, 0. So we're actually reaching 1, 0 for some reason. What was I trying to do here? Oh, okay. Gradient value. I think I got this. This should be zero R. There we go. Yeah, so this should be 0R. So before it was this one, but if you remember gradient, let's look at gradient. What is gradient? Right, gradient is the variable that corresponds to the gradients to the right of the current hidden layer. And we know that those gradients are just simply has the same size as the neurons to the right of the hidden layer. So if it's in the form of a matrix, it will always be a matrix with one row and left neuron size columns. So the row will always be 0, and the row will always be 0, the first row, and the column will be the R, right? The row index for the weight matrix. Okay, weight matrix is the weight matrix to the right, so the number of rows, that might be a mistake then. The number of rows will be the number of columns here to which it spans out. Might be a mistake here. I think this should be C. Yeah, should be C. So the number of rows will always be 0 for a gradient variable. The column index will be the same thing, right? It will be the same column as the weight matrix, where in weight matrix here, let's highlight this. Weight matrix here is the weight matrix to the right of the hidden layer. So if we're here, okay, the weight matrix is this one. So the number of weights that span out of this hidden neuron will be equal to the number of columns in the gradient for the previous gradient value. Some p set val blah 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 and push everything. Okay, so we have new weights there. Actually, you have that as our last function. And we'll see. Done with backprop. Make run done with backprop. Alright, so now what we want to do is we want to set the new weights as the new weights, the looking at our neural network, that should be the current weight matrices. Okay. So we've been pushing the new weights in reverse order, right, from right to left. In fact, we can check the size of the new weights after the back propagation. It should be equal to the, let's say, new weight size. It should be equal to the current weight matrix, right? New weight size is new weights dot size, and then we have old weight size is this weight matrices size. Okay, so they have the same size too. So now what we want to do is we want to set new matrices value is equal to the reverse of new weights. So we say new weight matrices is equal to new weights dot reverse. No, I'm only kidding. I forgot the reverse of the reverse function of a vector. It's something we can improve. See, if you don't have a reverse function, maybe it suggests something. Reserve. No, not reserve. Anyway, we can manually do it by looping through int I equals this, or rather new weight dot size minus 1. I is greater than or equal to 0. I minus minus, and then we say this weight matrices. Now, how do I reverse a vector? How do I reverse a vector? I need to search it. Wait, hang on. We just search real quickly the function of reversing a vector. Reverse vector C++. So I'm currently at home and I only have my data plan in my phone for internet. How do I reverse a C++ vector? See this? Right, so this has been quite a journey. Can I use I? I don't think I can use I. Yeah, I can use I. Let's wait for it to load. Alright, so okay. Okay, so apparently there's a reverse algorithm from the std namespace that we can use. So I'm gonna try that out, but I have to include it in the header file first. So let's say something like include algorithm. Right, so to reverse a vector, this is new weights, which is what we want to reverse. We say std reverse, or I don't think we need to include the std declaration here. So as reverse new weights dot begin new weights dot end. And just to make sure, for int I equals 0, I is less than new weights dot size I plus plus. We'll say new weights. We'll print out I. Okay, so we know where we are. And then we'll say new weights. Since these are a vector of matrices, we can say new weights at I print to console. Right? So this is the reverse. This is the original. Then we'll see if it actually reverses after calling reverse. Okay, so this is just to check it. Alright. Okay, by compiling, I'm just printing out the contents of new weights, reversing it, and then printing out the contents again. Okay, it's pretty ugly. So I can just see now it's reversed. It's a nice border. Okay, whatever. Right, make it, run it. Yeah, so apparently it reversed. Well, once reversed, then we can simply set the weight matrices to the new weight matrix. So after reverse, we can say this weight matrices equals new weights. And that's it, I guess, for backprop. Now to test if it actually works. So what we want to do is we want to keep on training the network, right? And let's just say that the input will remain the same, right? We want to keep on iterating the process of feed forwarding, setting the errors. I'll comment this out first, and then getting the total error, and then performing backpropagation, and then performing that same function of feed forward, backprop, right? Okay, just to see the high level overview. So we feed forward the network using the current input, and the target is the same as the input because we want to learn how to reconstruct the input of 101. Set the errors after the feed forward. Use those errors to do the back propagation. Well, actually, we can even shorten this. We can say that after doing the feed forward, okay, after doing the feed forward in our back propagation algorithm, we can call set errors there so that we actually have an error value. Right? So we say this set errors. Right? Or yeah, we can leave it as is. So so this process of feed forwarding, setting the errors, and back propagating the network is the training process, right? Then we get a total error. It should be here actually. Okay, so so let's try that out. We'll try to train this network 5 times. Okay, using the same input and using the input, same input, and the target as the input as the target. Okay. Okay. And we'll add a label. We'll say epoch I. Right. So now our network is actually training from an error of negative 0.80729. We have an error. It actually lowers. It tries to approach 0. Right, for each epoch. Wrong spelling for epoch. With this H right there. Let's try that again. Let's increase the training now to 20 iterations. Right, so as you can see, the error grows smaller and smaller with each pass of our feed forward and back propagation. So it slowly approaches 0. We can even increase that. So let's say we iterate it 100 times. See? Of course, the weights are randomized initially, but we can see that it's actually going lower and lower. Alright, iterate a lot of times. You can see that it will slowly approach 0. Right, you can see the values going lower and lower. So the network is trying to be better and better in terms of minimizing the error function by the error value by using back propagation. Okay, so the time now is 2:20. I think it took around 2 hours to actually create this video, or even more than 2 hours to create this video. So I'll stop there, and it's actually quite a bit. So I'll re-explain the back propagation algorithm in the next video. But for now, I guess this will do. The back propagation algorithm will have to do. We can improve it. There are a lot of room for improvements for this type of code. But for a live coding session, for a simple afternoon hack, I guess it works. So that's it for this devlog. Before I end the video, I will commit these changes. I'll say initial backprop function. Okay, so that's it for this devlog. It was quite a long process, but I guess we implemented the backpropagation function. Ending devlog now.